change in schedule. I was supposed to start at 7:30. So. Okay, that rolls. Do you hear me? Is that,
no.
Hello?
Yeah.
Okay. Now this is very loud. All right. Well, good evening. My name is Nasser Manesh. Thank you very much for joining us tonight. By way of introduction, I'm a member of the operations team at Altiscale. We provide Hadoop as a service. I've been working on Unix systems and managing Unix systems for the past 25 years. Right now my focus is scalability of multi-tenant Hadoop systems. As a part of that, the specific project that I am currently working on is compute bursting and elasticity of Hadoop clusters using Docker containers. My email address is on the screen if later on you want to ask questions or be in touch. I don't have a Twitter account. There's not much to say. Before we start, let's do a show of hands to get a better feel of the audience in terms of segmentation. How many of you are developers? Okay, about half. How many of you are doing operations in DevOps? About a third. Do we have any people that are users of big data applications, data scientists, people that use reports, Hive, Big, stuff like that? Okay, a few. Very good. The other question, how many of you are using Hadoop today? Okay, more than half. And Docker? Quite a few. Very good. Okay, so let me begin by telling you how we operate our clusters, which will sort of segue into why we need Docker and what we do with it. So Altiscale provides Hadoop as a service to customers. We do not provide a general computing infrastructure. We're not like Amazon AWS. We do not provide servers or nodes to customers. We provide HDFS and YARN. So people basically come in, install their applications on top of a ready provisioned Hadoop cluster and run their programs, load their data, and do their queries and modeling and recommendation engines and so on and so forth. In fact, as you see here, we provide a workbench that people log onto, and from there they have access to a cluster with node managers and data nodes and everything. What they get is specific usage of their cluster in terms of CPU cycles and storage. So a customer that, for example, has a 20 terabyte data set gets 20 terabytes of HDFS storage, which, as you can imagine, translates into about 60 terabytes of raw storage, given a replication factor of 3, which is the default that we're using. They do not care about nodes. They do not care about machines going down or going out of service. That's stuff that we take care of. They just run their jobs. Now, we do this on bare metal hardware today. We use purpose-built machines, specifically built for Hadoop operations. So a typical machine in our data centers has anywhere from 48 gigabytes to 256 gigabytes of RAM, anywhere from 8 to 12 4 to 6 terabyte hard drives, with a specific network design that is built specifically for Hadoop and very high throughput operation between the machines. So it's expensive hardware. In order to scale, we need virtualization. So these machines are very, very capable. And as you can imagine, probably many of you who are using Hadoop know that the jobs that run on a Hadoop cluster have I should call it a seasonal nature. For some people it's weekly, for some people it's monthly. It depends on the type of job that you run. Some people do modeling, so data comes and sort of is added, and then at some point a modeling job is run. For some people, they do end of quarter sales, they do end of month sale. For some people, it's more real time. So the nature of the jobs dictates certain patterns of using the Hadoop cluster. So, and then people and the companies are all across the globe. So we have people that are doing this in California, we have people that are doing this in India. So day and night. If we can virtualize the machines that we're using for these clusters, the result is that we can use the same hardware to serve more customers. So it's more efficient, and at the end of the day, it's more profit for the business. So this scalability requires a level of virtualization so that we can use the same hardware for more than one customer. Now, virtualization comes in two general flavors. There's the hypervisor model, or the virtual machines that the way traditionally by VMware and Xen was popularized and people know about it. So in this model, can I step on here? Okay. You have a host, and then you have a hypervisor layer, such as VMware or Xen, and it gives you virtual machines. Each of those machines run their own operating system, and then on top of it, the application. And then you have the container model. In the container model, the host OS is the operating system that is serving everybody. And that operating system has means to provide these partitions of applications so that each application is isolated. Naturally, what is happening is that here you have a lot of overhead because you are running multiple copies of the operating system. So for a lot of applications, including what we do, this model is not the preferred way of doing it because of the overhead. We really optimize the usage of the hardware. Every bit counts, every CPU cycle counts. And we're talking about scale, right? A few cycles of one core multiplied by 48 cores on one machine multiplied by about 1,000 machines becomes something that you start caring about. So we prefer to do that model.
The previous slide.
Sure.
In the second diagram where you have the two yellow bars below the app, what is written on it? Just above.
Oh, sure.
OS.
So this is binaries and libraries.
Mine is-
Yes, just abbreviated. Binaries and libraries that those applications require. Which, as you notice, I'm actually glad that you pointed that out, because you see that these applications, which are sort of instances of the same application, share the same binaries and libraries because it's all hosted by the same operating system, right? So less overhead. Now, there's been a lot of development over the years for containers. Some of you might be familiar with Chroot, which is a traditional Unix tool from many, many years ago, where I could Chroot a process, basically giving it a limited view of the file system. That would be the world of that process in terms of the files that it would see. But that's pretty much the extent of what Chroot does. And then in FreeBSD, a mechanism was developed in 1995 called BSD jails. With jails, you can actually create a sandbox for a process, give it its own networking and everything. The main limitation here is that you don't have resource limits for a process. And then other technologies were developed over the years. But as you see, containers, as we were just talking about, meaning that the operating system running on that machine can provide that type of virtualization for the applications, for the processes, is something that has existed in the Linux kernel since 2007. So that's many years ago. Before we continue, it's kind of important to understand what the container gives you. How many of you have seen the movie The Truman Show? Okay, so you remember what happened to Jim Carrey. He was living in a world where he didn't know that something outside existed. That's isolation. The key here is that a process that is isolated will not know that there are other stuff outside of its worldview. This is in contrast with limiting the resources available to a process. A process may very well know that it's limited in using certain things, such as the network bandwidth or the CPU cores. So it will know that there's more bandwidth available, it will know that there's more memory available, but a portion of that is accessible to this process. Containers generally give you these two things: resource limits, which translates into what we call the namespaces in the kernel, and isolation, which is the namespaces, and the resource limits, which is called C groups or control groups in the kernel. So these were implemented in the Linux kernel, and then there were tools that were built around it to give people ways to containerize applications and processes. LXC, short for Linux containers, is one such example. And it has been well developed. It is actively developed today. However, it is very hard to use. The interfaces to LXC require a person to read a lot of documentation. They need to be very familiar with how Unix works, and it's not easy to implement it in a system. Google released Let Me Containerize That for you, LMCT5. Again, because it's actually a very robust system. However, it inherits part of the stuff that Google has been using for their own containerization in their own infrastructure. It's hard to use. It's very complex. OpenBZ, same thing. It's actively being developed today, but again, it is hard to use. The thing that happened with Docker is that all of a sudden, some people sat down and came up with a nice, easy to use interface, which is very, very developer friendly. So it's a matter of minutes for a person to download some stuff and create a container on the fly on a Linux machine. It doesn't really require a lot of expertise. It's a matter of reading a couple pages of documentation, and that's it. So containers were popularized when Docker came about. There's always a catch. Docker is easy to use, and developers love Docker. However, it's not very friendly when it comes to operations. It's not very friendly when it comes to production systems. Simple example. First thing that the operations staff need to deal with is that something goes wrong, we need to check the logs. if you try to check the logs in a Docker container, you will realize that they are shared with the host. So you can't actually see what is happening inside the container. The networking that comes out of the box with Docker is very easy to use if you just keep it that way. And for a lot of people, especially people that are doing development, people that are using Docker to, for example, create Jenkins jobs to test something, that out-of-the-box networking works. Flawless. And that's part of the beauty of Docker. It makes things simple, right? But if you want to do the same thing in an enterprise environment where you need a lot of optimization for your networking, you're using specific types of routing, specific types of packets, then the Docker networking will not work. And once it doesn't work, getting it to work is not easy. The other thing is that Docker has been created with the idea of containerizing applications, meaning that typically you give Docker a process to containerize. And that process might have children, so it ends up being a process hierarchy. But at the end of the day, we're talking about a process, a few processes, and so on and so forth. It is not built to give you a virtual host. So even though there's networking integrated into Docker, once you want to look at a Docker container as a host where you do generic things, then you will run into problems. And most of these problems are race conditions. Because, for example, you start to deal with networking issues in Docker, and the way things happen in a certain physical host, they have a certain natural order. But if it's a Docker container, things can happen at any given time. You can add a networking interface to a Docker container when you don't know if the networking interface has been, the networking layer has been enabled or not. So there's always a race between stuff that you do to the container from outside versus things that are happening in the container, which are being done through the typical RC system or systemd or whatever tool that you're using for starting up stuff inside that container. Yes?
How is that different with any other hypervisor?
Well, if you're looking at a hypervisor, the hypervisor is actually giving you a machine that by itself is not doing anything, right? So you're actually booting up a kernel in that hypervisor. Once you boot up a kernel in that machine, that kernel goes through the typical hardware probe and everything which is being simulated by the hypervisor. So the same natural process of things shaping up and booting up in the hypervisor applies. Here, you don't have a kernel, right? You're just starting a process in that container, which is fine if you're doing just that process, but if you're looking at this as a generic machine, then there are some things that are missing. You need to inject them into the container, and those things do not necessarily happen in the order that you expect them to happen. Okay. So, things that we are looking at and we need in order to be able to use Docker for a production environment are this type of requirements, and these could be different for different applications, but generally speaking, these apply. One of the things that becomes important, it's kind of given when you're using a physical machine, but it's not coming so naturally when you're using a Docker container, is predictability and reliability of the environment. Specifically because of the race conditions that I just mentioned, things happen kind of sort of different in different containers once you start doing software installations in those containers and run stuff, especially when it comes to networking. Performance and security is another interesting aspect of this, because Docker by default uses a certain type of file system, which is a layered file system. It's called AUFS. And if you're not careful, your files are going through a different way of being written. It does copy and write, it does different layers, which is very different from what you're used to on a physical machine, a typical ext3 or ext4 file system. So you get very different performance characteristics. So you need to be careful about what kind of file system you're using for what, and how you let your Docker container know when to use AUFS versus when to use ext4 for your data. Security is also important, because if you're securing your machines, using something like IP tables, and typically if we're talking about an environment like us where we have about 1,000 machines, obviously we have automated ways of configuring these IP tables on these different machines based on their roles. Now, your Docker environment treats IP tables differently, because IP tables has interfaces into the kernel, and that kernel is being shared by the containers running on that machine. So it's not trivial to set up IP tables on your Docker containers and expect it to behave the way a physical host does. I talked about networking. For example, one of the issues that we ran into, which was very interesting, is that the first time that we ran a Hadoop cluster on Docker containers, we had a performance drop of about 50%. And there were a number of different things involved, and I don't want to go into all of the details, but one of them was that on our network, we're using jumbo packets. So these are Ethernet frames that are bigger than what you typically do in a non-enterprise environment, because Hadoop pushes a lot of data. So an Ethernet packet of an MTU of 9,000 gives you a performance of much better than the default 1,500. Now, you do this in Docker, you lose that capability for doing an MTU higher than usual. So now you need to start tweaking things to get your MTU back. So those issues become a problem. Metrics and monitoring. Most of the tools that you use for collecting information from your host today, I shouldn't say most, but a good number of them are not container aware. So, simple example, if in a Docker container you just run a DF, what it shows you as the root file system is the root file system, I mean in terms of space, is the root file system of the entire machine, not the Docker container. You run free to see how much memory you have available, what you get is the entire machine. So collecting information about the resources, disk utilization, and so on and so forth is not trivial, simply because your tools are not changed to understand C groups and count what is happening with the container. Now, for a developer, these are non-issues, right? You just run your code, you're just developing. But for a production environment and for the operations team that is dealing with these issues, when you're dealing with a situation where your Hadoop is running out of memory, your node manager has died because of a heap that just grew too fast, and you need to troubleshoot these things. Being able to get these bits and pieces of information from your machine is essential. If you don't have that, you cannot troubleshoot. The delivery infrastructure for Docker is also another thing that you need to be careful about, and I'll talk about that in a couple of slides down the road. So, Aside from all of those issues, which are hard to tackle but not impossible, there's the question of how you actually deal with Docker in the world of Hadoop. Those of you who are familiar with Hadoop know that Hadoop 2.0 and 2.x has a model where your resource manager, YARN, has an application master that talks to the node manager or any of your physical machines to ask for it to launch what Hadoop calls containers. Now, these are not Linux containers, these are Hadoop containers. It's basically an abstraction to specify the amount of resources, memory and CPU, that a node manager needs to get a certain job done. It's actually a very nice integration to have Docker take over that part of Hadoop. Okay. Meaning that when your application master talks to the node manager to launch a container, it is possible to have it launch a Docker container. Now, if you do that, okay, we're not at yes but yet. If you do that, you get a bunch of good stuff. For example, you get a much finer grade resource limit on stuff that you're doing. Remember C groups, right? With C groups, you can limit the amount of memory, you can limit the amount of CPU cores, and so on and so forth. That is allocated to that job. And it means that Hadoop doesn't have to worry about those details. Docker can take care of that. It's going to be much more secure. And then there's this, yes, but it's not easy. Doing this needs changes both to Hadoop and to Docker at the code level. And people are working on it. Actually, Altiscale has staff that are working on these issues, both on the YARN side and on the Docker side, contributing back to the community. But it's a lot of work. There's a famous JIRA, for those of you who are doing development, in YARN 1964, which is specifically dealing with issues around integrating Docker into YARN. But as a result of that, this is not readily available. You can't do it today, even though in theory it's a very, very nice idea. So there's an alternative. Instead of trying to get Hadoop to launch Docker containers as its own containers, you can try to create Docker containers as virtual hosts, effectively taking place of the nodes that you give a Hadoop cluster, and then run your processes, your Hadoop processes inside those containers. Traditionally, what happens is that on a typical slave node in a Hadoop cluster, which is, as you probably know, it's like 99% of your Hadoop cluster. On a Hadoop cluster, you have a main node, and you have a resource manager, and then the rest of your nodes are the slave nodes, which run two main processes. The data node, which is your HDFS agent, dealing with the disk and I/O, and the node managers, which are taking care of the actual jobs that are running, the YARN part of the Hadoop environment. Now, traditionally, in a typical Hadoop cluster, you see that the data node and the node manager are paired. Sorry about that, misspelling. Are paired and they run next to each other on the machine. So if you have a 20-node Hadoop cluster, setting aside 2 nodes for the node manager, your resource manager, each of those 20 nodes are running a data node and a node manager process. Now, what you can do is that you can create containers on the physical machine, let's say 2 containers, and launch your data node process in one of those containers, and launch your node manager process in the other. Effectively, by doing this, remember namespaces and isolation, you're isolating your data node process, which is doing the disk stuff, and your node manager, which is doing the jobs. Now, you can launch additional containers on the same machine and launch additional node managers in those containers. Effectively, what you're doing is that you are creating additional node managers that, when a machine is not that busy, can take over and use some of the idle cycles of this machine and process jobs for another machine. So when a machine is heavily used, that other container is not doing anything, it's just sitting there. And when that machine is not being utilized, the Docker container on that machine runs a node manager, which is actually doing jobs, just taking advantage of this free CPU cycles that are sitting here, and do jobs for another application master. The good thing about this model is that if you can get the infrastructure part of it right, it's just like machines for Hadoop. So it doesn't require changes to Hadoop, almost none. And also it's repeatable because you're just launching containers with specific processes in them, node managers or data nodes. And because it's just repeatable, you can automate it. And if you can automate it, you can scale it, which is the name of the game for large clusters. So this is what happens on a typical physical machine that I was describing. Here on this machine, we have 2 containers, and they are sharing a stack of stuff. It's the Linux kernel and then the stuff that we run. We use Chef for managing our infrastructure. So we run a series of different cookbooks to prepare this node for running containers, and then typically 2 containers run on this machine. If you look at one of these containers, what you see is kind of very, very similar to what you see on a physical machine. So the cookbooks are run to prepare this container. At the bottom, what you see here is sbin init. So we use init as a process launcher on that machine to make it as similar as possible to a host, which is not easy. Like I said, there are issues that come with this. There are race conditions. That's the type of technology that we have developed to work around this. But once you can run init inside that container, what happens is that you have all of your RC system, all of the services that you have check config for Hadoop or monitoring or other stuff that you run in that host that you used to deploy to a physical machine, you can now deploy them to this virtual machine that is being created through Docker. And your data node process is running inside that container on top of your sbin init and the other stuff. The other container similarly does the same thing, it just runs your node manager.
I have a question. From the previous, not this slide, but the slide before that, you explained it, but I didn't quite understand.
Sure.
In that, where you were saying is isolate the data node and node manager. And what does that mean? Is it like on different machines?
Well, think of it this way. Actually, let me come back to this slide. We're talking about 2 containers running on the same machine, right? So this is where isolation comes into place. This container has its own view of the world. It doesn't know anything about the stuff outside, and this is running the data node process. This other guy is running a node manager process. So in that sense, they are running in 2 different virtual machines, but they are running on the same physical hardware. Other questions? Okay, so
I understood question was, when you say isolate,
Right.
what does that mean?
Meaning that they don't know about each other, meaning that each of them has its own network interface, each of them has its own IP address. It's effectively as if you are running these on two separate pieces of hardware. They do not need to know about each other.
But that comes with containers anyway.
Yes, that is why we're using containers here. That is the point. So what I'm saying is that, so remember, we talked about a model in which you are trying to get Hadoop to launch containers for you, right, to get that isolation. The other model is to create the containers, to get that isolation that the containers give you, and then run your different Hadoop processes in those containers. Now, what happens is that, as I mentioned, you have additional node managers that effectively are floating around depending on the load of the machine. And this is where your automation comes into place. You can have tools that are watching your clusters and the machines, and when there are machines that are idle, they just take advantage of those node manager containers and get jobs done on those machines. Now, each of those containers gets its own resource limit. So these two containers, even though in this picture is a little bit deceiving because the containers kind of look like the same egg. They are not. They are actually very, very different in the sense that your data node container is the one that is responsible for disk I/O. So it gets all of the disks, almost all of the disks of the machine. But it doesn't need a lot of cores or memory. The node manager containers, on the other hand, they use a lot of CPU cycles, but they don't do disk. Not that they don't do disk at all, but not anywhere close to the data node process, which is kind of nice because this way you're slicing that machine and giving certain resources to certain containers based on their usage. Now, this disk allocation is kind of important because even though most of your I/O is done by the data node process, you need to set aside a portion of your disk for the node managers. And the reason is that when you run MapReduce jobs, you need disk space. The node managers need disk space for the shuffle phase. They store a lot of data, temporary data, locally as they go through the phases of map and reduce. So, and now think about, again, an enterprise-grade machine with, let's say, 12 hard drives that is being used in a picture like this, right? What do you do and how do you provision those disks for these containers? The right way to do this is that sorry about that. Okay, the right way to do this is that you choose a layout that is repeatable for your different types of hardware, and the best way that this works is that you partition every single disk of the machine in a way that you give a small portion of that, or you allocate a small portion of your disk to any node manager related stuff, and then you allocate the rest of the disk, which is a very large portion, to the data node stuff, to your actual HDFS I/O. Now, the way you expose this to your Docker containers is important. As I mentioned, Docker itself by default uses a file system type that is not suitable for this type of heavy write operation. So what you do is that at the host level, at the host operating system, you create these partitions and you put file systems in these partitions and you mount them. And then, horizontally, you expose those mount points, not the devices, the mount points as directories to Docker. Docker can mount directories, and you can pass directories to Docker on its command line. So the container that runs the data node gets a different set of mount points compared to the container that runs the node manager. The data node container gets the bulk of those huge file systems, and then the node manager gets a set of file systems that are much, much smaller, but still big enough for the node manager operation, for the shuffle phase and reduces and so on and so forth to be able to do whatever they need to do on disk.
Question.
Yes.
Are you saying that you're passing the volume information to the container and that's being used by the data node, not the other,
Exactly. Yes.
data representation?
Yes, and there's a reason for that. You want to do that because if you step back and look at the big picture, these machines are being used in our environment, at least, by different customers, right? So you want to make sure that anything that is being accessed by container A remains within the realm of container A and never is exposed to a container B, which might be running a job that belongs to customer B, right? So one of the things that we're doing here is that we are isolating the data that belongs to different customers by giving them and serving them through specific containers. So yes, the container never sees the actual Unix device of that file system. They don't have access to it. They have access to a specific set of directories which are passed to Docker as volumes, and those volumes are provisioned in a certain way for the data node versus the node manager.
Also because of the 10-gig limitations that you prefer to choose volume, or?
Not really. In our case, the issue is that we want to have minimal overhead by Docker. So if these file systems, especially in the case of the data node, are typically somewhere around 4 to 6 terabyte size, right? And we're talking about 12 disks on that machine, so we're talking about 4 terabyte file systems. So we want a minimum amount of overhead by Docker. So we want the actual I/O and everything being managed by the code of ext4 that the host operating system is running. And Docker is just passing bits. It's not doing anything else. And it cannot access anything else beyond that. Yes?
How do you prevent the disk not seen inside the Docker? Group settings, or how do you?
So when you run your Docker container and you're only giving it directories, it will not see any of the devices. If it's not seeing any of the devices, I'm talking about the block device that represents that disk, it has no access to the disk. So it's implicitly done by the C group because that C group is generally limiting that process. But the fact of the matter is that because we're just giving it mount points, it has no access to anything beyond that. So we only give it specific mount points that at the operating system level are pointing to specific partitions and file systems on the disk. Yes?
So is it a preferred method, or you like to have a disk exposed to the data?
Well, it depends on your use case, right? In our case, the key issues are security of the data, because it's a multi-tenant environment and we have multiple customers running stuff on the same hardware, and low overhead. So we sort of delegate all of those to the host operating system, and we limit what the Docker container sees. You might have other cases, other use cases where you want your Docker container to actually see the drive or the file system. That's a fair use case. It's just not our use case. For Hadoop, pretty much, as far as I can tell, you wouldn't want Docker to see your devices. There's nothing to gain by that, let me put it that way. In terms of monitoring and metrics, this is one kind of tricky area We figured, after sort of playing with a number of different things, that because of the way we monitor our infrastructure, which I'm assuming pretty much anybody who's doing any serious Hadoop infrastructure has to do the same. You need to monitor your node managers and your data nodes to make sure that your HDFS and your jobs are in a healthy shape. You don't really need to monitor the Docker process itself. So Docker runs on that machine. If it doesn't run, if by the act of dying, it also kills your containers, you will know because your node manager and your data node are gone. If it's killed in a weird way that its children are still there, the children being the actual containers, you don't care because your containers are up and running. So in an environment like this, you don't really need to monitor the Docker process itself. However, the node managers in the Hadoop world use a certain methodology to check for the health of the machine they are running on. And based on that, they report back to your resource manager to sort of give it a view of how many nodes are available to do jobs on this machine. Now, the health of the node can be tricky in this case because you need to make sure that, so Hadoop runs a command line, and you can give it that command line to decide whether the host is in a good shape or not. If that command line acts differently, for example, looks for certain files in the file system between the physical host and the container, then Hadoop can get tricked into thinking that your container is, the host is down while it is up, or vice versa. So you need to make sure that whatever command line you're using for health check in your Hadoop environment works properly within that container. Now, commands do the same thing. It doesn't matter whether it's inside a container or outside on a physical host. What matters is that typically you do this, and by running that command, you check for certain files in your file systems. Remember that the file system view that the Docker container is giving to Hadoop is different than the file system that you have on the host. So the files that you might be checking for on a host are not necessarily there when you're looking at it from within a container. Now, you might need to mount those files as volumes under your Docker environment to be able to check against them and determine whether your node is healthy or not. The other thing in terms of monitoring and metrics is that for metrics and getting numbers from what is happening on your container nodes, as I said, the tooling is not there yet. So you don't have tools like free that can tell you how much memory your container is using and how much is free available to that container. Fortunately, very recently, Google released an open source tool called hypervisor, which does that for you. It actually does the hard job of going through the cgroups information stored on the host and parses that depending on the type of your operating system. This is done slightly differently on different types of Linux. So CentOS is different from Ubuntu, different from Fedora. So they have done this. They are finding the right information off of your cgroups information based on the type of the Unix that you're using, and they present that to you in a nice way. Specifically, they provide a REST interface through hypervisor, so your tools can actually query that REST interface and provide that information to whatever metrics infrastructure that you're using to collect data from your containers in terms of resource utilization. So information such as memory usage, CPU, some networking is currently available. Information about disk usage is not available. That's actually something that we ran into, and we have implemented at Altiscale. We're contributing back to the community. But that's a very, very nice tool for getting numbers about what resources your containers are using. Lastly, the delivery infrastructure is something that does not immediately come to mind, but it can become an issue. Docker needs what they call a registry, which would serve Docker images to create containers. Docker sort of packs everything that constitutes a container into a file, and a Docker container is created off of that image. It's kind of the way in Linux you create a process from a file, right? You run a file, you get a process. Here Docker gets that image, and based on that launches a process. Now those images are being served from effectively a file server, really. It's an HTTP server that serves files to whoever that is asking for them. This registry is very, very, very basic. It's not enterprise ready. There is no authentication. There's no replication. And the images are typically big unless you're just containerizing small applications. For us, a typical container image is somewhere around 600 to 700 megabytes. So again, think 1,000 machines pulling these images off of that registry, and we're talking about traffic, a lot of traffic. So depending on the geometry of your network, if you have, like we have multiple colo data centers, so the right way to do it is to definitely create a level of caching, and that's something that the Docker registry does not give you. You have to create that yourself. So you can use something like Squid or the Apache Traffic Server to create a layer of caching and cache these images close to where your actual physical nodes are to speed up the load of the containers. Also, authentication is important if these images contain proprietary software or stuff that are not supposed to be public to the world. You need to build security around your Docker registries. Yes.
So this registry for enterprise will be private for you, right? So why?
Yes.
In that case, why?
Well, so within an enterprise, you could easily have multiple groups that have different levels of access, right? So you have different levels of security. For example, ops people, in our case, the operations staff has access to certain things that other people do not. It's not necessarily malicious access, it could be accidental access, right? So you want to prevent that. There are levels and layers of security. So even if that host is not open to the world, even within the enterprise, a lot of times you need to protect things with authentication to make sure that there's limited, well-defined access to it. Again, for development, who cares, right? When it comes to production, there's all kinds of stuff. And interestingly, some of these are not necessarily even mandates of the business. It could be the fact that your business is providing services, like in our case, we provide services to other enterprises and they mandate certain levels of security. We need to be compliant with certain types of security, so for that reason we need to have those levels of security in place. The last thing that I want to mention, which is kind of not directly related to what we're doing, but I think is very important aspect of Docker, kind of less advertised, less known, but to me equally important, if not more important, is that aside from creating containers for resource isolation, one of the key things that Docker does, which has nothing to do with containers per se, is that Docker, through these images that we just talked about, provides a nice way of packaging things together, right? So from a release engineering point of view, you can install certain packages, certain release versions, and whatever that is supposed to be there for your environment, your software to work, all the right bits and pieces, into an image, and then freeze it as a Docker image, and there you go. You have an image that you know will work. So think of this as a new way of delivering software. Before, you used to do RPMs, right? And then there's the dependencies, or if you're developing using Ruby, you do gems, and then there's the dependencies, and this doesn't work with that version, that doesn't work with this version, and you end up with different versions of different things in your environment that sometimes work on a given machine, they do not work on another machine because just one package is kind of slightly different in its version. With Docker, you can actually freeze all of those different packages in whatever dependency tree that you're looking for. When you have done your tests, you have done your CI jobs, and you have tested and you know that they work, you package all of that together and you create an image, which is effectively an image of a machine that you know it will work. So this sort of creates a new opportunity in release management and better reliability in terms of how software is delivered, especially when we're talking about thousands of machines. So an interesting thing to think about. That's it. If you have questions, I'm here. I'll stay around for a few minutes after the talk, so I'll be happy to answer any other questions.
One question about the core OS. Does that solve any problem you mentioned here?
We are not using CoreOS, and the reason is that for us, we do a certain process for our release engineering which counts on a specific software stack, and we have well-tuned that software stack for what we're using, which is CentOS, right? So a lot of work has gone into handcrafting those layers of software that are put together. What we need is there, probably very, very optimized. What we do not need is not there. And we just deliver that to all of our machines. And now that we're using containers, we're delivering all of that exactly in the same fashion to all of our containers. So we do not want to use a different OS environment. We don't have a use for it. Again, for a different use case, if a group is starting from scratch, using CoreOS, perfect, but that's not us. Yes?
I'm not a big data guy, so this question may be a stupid question.
No stupid question.
So in the VM-based system, without the live migration or vMotion capability, is it any relevant to Hadoop kind of system, or you don't care?
That's actually a very good question. In the world of Hadoop, everything is created with fault, disaster, and mobility in mind. Basically, the point of view in doing a Hadoop cluster, if you do it right, is that if a node dies, who cares? Because some other node will just take over. If a node dies, the jobs that are running on that node at that moment will die, but your resource manager will just reschedule those jobs on a different node. So it's not migrating processes. It's not migrating virtual machines. It's restarting those jobs elsewhere, which effectively gives the users the same result, right? Now, that's the Hadoop side of things. With Docker, that's actually a situation that did not exist up until very recently. I'm actually looking at the person that developed that mobility. He's sitting right here from Google. He did a presentation, what was that, about less than a month ago, right? Yes. So at Google, they worked on this specific feature, basically using another open source tool called Credo, which migrates processes. Now, if you think about the way Docker works, containers are really processes, right? Limitations on top of it, namespaces, all of that. But at the end of the day, these are processes. So you can, theoretically, use a tool that is able to migrate processes to migrate containers. It's not that easy, though. There's a lot of gotchas and stuff like that that they have been working on, but that feature is close to release at this point. They are working with the Docker community at this point to add that feature to Docker.
What's the tool name?
I'm sorry?
What was the tool name?
The tool name is CRIU, C-R-I-U. That's checkpoint and restore user space. The migration concept is something that has been around for a long time, and traditionally it's been called checkpoint, meaning that you save a process, and restore, meaning that you launch that process elsewhere. Yes.
So you deploy Dockers on bare metal, right?
Yes.
So are you concerned about security? Because, I was in the Google meetup a couple of weeks back, and they said they still, Google Cloud, if you want a container, they still give you a VM and a container on it. The reason they, at least I was told, was for security, because VM is much more secure than doing.
Sure. By definition, that is true. Well, VM will be more secure. The question is Docker not secure enough? The jury is out on that. We're actively looking into it. I mentioned IP tables and things that come with it. So there are a few different aspects to this. One is your network traffic and how your IP tables is actually protecting your Docker container, right? And you can work on that to sort of beef up security from that point of view. The other side of it is bugs. We actually had one case where we found a bug in the Docker code that resulted in leaking stuff, which we were the ones that fixed that bug because we were the first company that ran into it. So is it secure? It's pretty secure. Is it completely 100% secure? Probably not. But that's for us and companies like us to constantly watch. Is Linux secure enough? You can always debate that. So it's that situation with Docker. We are actively looking into that. If we run into situations like that, we put resources on it to fix it and contribute back to the community because of that reason.
Yeah.
I want to follow up with the same question. So in terms of security issue, the example you gave is, the IP tables and networks. How about the memory? Because, if you look at two containers,
right.
At the end of the day, they're sharing the same physical memory space.
Yes.
There could be some, memory leak to another containers.
That is true. Theoretically, it is possible. So it goes back to the implementation of C groups, right? So if you look at how C groups are implemented, the actual virtual memory pages that constitute the memory of a container have different lists per container. So at the kernel level, these are separated. Now, yes, they are running on the same machine. If your kernel doesn't have a bug, there shouldn't be a memory leak because the kernel is maintaining separate lists for those memory pages. Let's put containers aside for a moment. A Unix system is a multi-process system, right? Are there memory leaks between the processes on a Unix machine? Theoretically, it is possible. But right now, we're not operating with the assumption that that happens because we're confident enough that the kernel takes care of that, right? It's the same situation. When with the C groups code being in the kernel since 2007, that part specifically, the CPU C groups and the memory C groups are in a good shape in that sense. Could there be bugs that would result in something like that? It is possible. Is it probable? No. Yes.
So in your cluster setup, typically how many different containers have been running in the cluster?
So for us, think of it this way. Hadoop is about big data, right? If I have a machine that has 12 disks of 6 terabytes each, I want to give all of that to my cluster. So typically on any given machine, you only run one data node process because there's really no point of breaking down those disks and give them to different customers. Those disks being served off of the same controller and all that will be utilized by a big data job. So since the patterns are heavy usage, for us there is no point to do any data isolation and break down a host and give half of the disks to customer A, half of the disks to customer B. What happens is that you give all of the disks of, for example, 15 nodes to customer A, and all of the disks of another 20 nodes to customer B. And remember, the data needs to be there at rest, right? So when they're not doing stuff, their data needs to be there. It's not like compute that they can easily migrate around. So in that sense, we run only one data node process on a physical host.
So if you have more disks, then you have the leverage to partition.
Sure, I mean, if you have more disks, yes, but practically, again, for the case of big data application and serious Hadoop clusters, you don't really run into that situation. Typically, it's the other way around. You run out of nodes and disks for the data that comes in. You don't want to break down a disk and share it between different customers, especially because you will lose performance with that. The performance characteristics of jobs from different customers could be different, and you don't want that head to go back and forth competing for the jobs of two different customers. Now remember, this is something that a lot of people do. You look at Amazon. Amazon is effectively doing that, right? Amazon is giving you a generic computing infrastructure, which works for everything. You can run web servers, you can run application servers, you can run Hadoop jobs, right? So because they are providing a generic environment, they need to do this. They need to partition disks and everything between different customers, of course. For us, because we are doing a special purpose service, it's only Hadoop, it's only big data jobs. We're optimizing everything from our processors, from our disks, from our network. Everything is optimized. So from that point of view, for us, it doesn't make sense to break down disks between different customers.
Is there any reason that the name node is not in the container?
Time. Getting each piece of this to work takes engineering resources because of all the gotchas that you run into. So for us, we focused on the 80% problem, which was the node managers and data nodes, because that's the bulk of your computing, right? For any given cluster, you have 20, 30, 50 nodes of those slave guys, and then one node manager. I don't gain much by spending resources on how do I want to put this guy in a container. Once I do a data node and a node manager, all of a sudden I can containerize a lot of nodes. So it's a matter of time. Probably this time next year, if we talk, our name nodes will be in containers soon.
Yeah, the reason why I asked was like if you specifically got into any issues.
No, it's just the behavior is different. As a result of that, we just did not spend time on it. It's a simple matter of resource allocation from an engineering point of view. There's no technical issue keeping us from doing that. Yes.
I presume you have hundreds of containers in your data center, or even thousands.
Yeah.
How do you use Kubernetes or Mesos? How do you manage, schedule?
We're using Yarn, right? Remember, everything that we have is Hadoop. So in that sense, we don't need to deal with different frameworks for which we would need something like Mesos to do it, sort of another higher level of scheduling. We're using Yarn, and it's working pretty well for us. Again, it's not necessarily the right answer for everybody. For us, being a Hadoop shop, everything Hadoop, Yarn works perfectly.
So you also don't use Kubernetes?
Not at this point. We'll probably look at it more than anything to just to see the differences, see if there are ideas and stuff, or parts of it that we can use, but I don't see us using that as a production environment. Yes?
We were talking about network optimization, and you mentioned your ability to change the frame size, the number of packets you can send to you. What other optimizations that you think you are doing in your environment?
So for us, for example, the distribution of route tables is something that is very, very different in a complex mesh network like us. We use OSPF. We don't use a typical route distribution algorithm. So we have more traffic in terms of route distribution, but everybody knows about everybody in the network, right? So for that, you need to run certain daemons on these machines to be able to get the routing information, redistribute the routing information. That's another optimization we do. At the switch layer, we use a leaf and spine architecture. So we pre-compute the number of hops that these machines need to take to get to each other, so that the distribution of the nodes of the Hadoop cluster is even if the machines are not in the same rack. Things that a lot of other vendors do not need to do, because they do not need to optimize for this specific purpose. For us, again, because it's big data, we're moving a lot of bits. Moving a lot of bits needs optimization at these weird levels.
You also talked about you could use containers as a great way to do image distribution.
Yes.
Are you also looking at multicast trading?
Not at this point. That has not become an issue. We might at some point. Not today. Not today. Yes.
Are you using host networking for your company?
We pretty much the same way all of the networking that comes with Hadoop. With Docker. We took all of that out, and we are doing our own networking using OpenVSwitch to provide networking, software-defined networking on the host, but not just a regular networking, and mesh these containers from different nodes to each other to create a container.
Yes, Hadoop identifies the data node through the host name.
Yes.
So you are essentially using the same host name.
We have done other optimizations to sort of work around that, because what happens is that once you put these into different containers, now technically speaking, these are two different hosts. So from the point of view of Hadoop, locality is out the door. It counts them as two different hosts, not the same host. So it's not like it understands that, okay, I'm a data node, or I'm a node manager that happen to be local to this data node, so let me just ask the data from this data node. That just does not happen in this scenario. So we have done other optimization to work around that, including a couple of patches to the node manager code to make sure that when they are local, they can take advantage of the locality. Yeah.
Are you by any chance thinking that as an open source?
Not right now. Probably we will. But although there's been work that is done on this particular issue by VMware. So there are patches that are available today. We took some of those concepts, we did our own in-house development, and we have done things that it's not a matter of keeping proprietary software. It's working well for us, but in order to put it back into the Hadoop core, it needs to become more generic, which we haven't had a chance to do. We have done something that works well for us, and that's the extent of what we have been able to do. When we can make it generic enough, then we'll obviously contribute back to the community. I think we're running out of time. Any other last-minute questions? Thank you very much.